All right, we are going to go ahead and get started. I know we have some folks still rolling in, but we want to give all of our amazing speakers all the time we can. So thank you to everyone who's joining us. We have just a few announcements as you all get settled. First, we are recording this session and it will be available in Whova, our conference app, within 2 weeks after the Congress ends. If you'd like to ask our speakers any questions during this session, please use the Q&A area to the right of your screen. The chat window is where you can engage with other attendees. And we kindly ask that you keep your mics and cameras off during the presentation and follow the presenter's lead on when to engage with cameras and microphones. I think we are ready to get started, so I'm going to hand it over to our speakers to start and introduce our moderator today, Louise. Louise.
Thank you so much, Sama. This is Louise Loudermilk. I'm a research ecologist at the Southern Research Station with the Forest Service. I'm located in Athens, Georgia. We put this session together with Zachary Robbins and Rob Scheller from North Carolina State University. And this was based on all the work that had been going on since the 2016 fall wildfires in the southern Appalachians. And so I definitely don't want to take any more time from Mike. Mike, if you want to start uploading or presenting your first screen there. Mike Stambaugh is an associate professor from the University of Missouri, and he's going to be talking today about historical fire and climate. So take it away, Mike. And so, by the way, there is going to be a, time for questions at the end of each talk. Thank you. Mike, go ahead whenever you're ready.
Okay, try this again. Okay, thanks for inviting me to give this 15-minute talk on such a small topic of historical fire regimes in the southeastern United States. I'm going to do my best to cover, I think, some highlights, but certainly there's a lot to be covered here that I just am going to have to gloss over. The title of my talk is Historical Fire Regimes and Climate Associations in the Southeastern United States. My co-authors are Joe Marshall and Aaron Abadir here at the University of Missouri, as well as Dan Day with U.S. Forest Service Northern Research Station. So just a general outline of where this talk is going to go today. I'd like to provide an overview of southeastern U.S. fire regimes, mostly based on historical fire information, but some supporting information from other sources. I'm going to give some examples of historical fire regime data that I think provide some new insights to what the past may have been like in terms of fire and changes in fire regimes, moving from the coastal plain into the Appalachians, Cumberland Plateau, and likely into some other regions. And then along the way, I'll be sharing with you some of my thoughts and interpretation of what I think this all means. So many experiments, models, experts, managers kind of agree or conclude that southeastern U.S. region has some of the most frequent fire regimes of the United States. Here we see on the top left, Cecil Frost's kind of classic map of pre-settlement fire frequency, the Southeast having fire intervals, particularly in the coastal plain and Piedmont, anywhere from 1 to maybe 4 years in frequency, and then moving up into the southern Appalachians of maybe increasing that into 10 years or so. The top right here is the PC2FM fire in physical chemistry model that Rich Guyette, myself, and others worked on. Very similar results showing just vast areas of very frequent fire regimes throughout the southeastern U.S. pre-1850. And then lastly, at the bottom, another just different line of support here for frequent fire from the land fire mapping product, showing vast areas of the southeastern U.S. with very frequent, almost really unbelievably frequent fire in the region. So just to highlight some of the unique characteristics of the southeastern U.S. and its fire regimes, front and foremost is this extensive frequent fire region. It's not just frequent fire, it's extensive frequent fire. I think the Southeast is really unique in that it's a strong transition from continental climates into subtropical climates. Globally, that's fairly unique. In the top right, you can see some circles of humid subtropical climates throughout the planet. Those that also include lack of a pronounced dry season. And the southeastern US is really unique in North America for that reason, matching up with maybe the Cerrado and Atlantic forests of South America, some parts of Western Europe, and then southeastern Asia. Interestingly, a lot of these maybe analog types of climates are on the eastern sides of continents and adjacent to oceans. The Southeast has a strong oceanic influence, particularly through humidity and constant temperatures throughout the year. We have year-round fire potential, really, if the weather can present itself. Within the Southeast, we do have the interesting kind of inset of the Southern Appalachian mountain regions. Interestingly, a deciduous forest region in combination with pine in terms of a cover type. And also interestingly for this mountain region is that it's surrounded by presumably very frequent fire regimes in more lowland areas. The Southeast was the region of early European contact, so it's kind of unique in that way that some of the European influence was early here. It's relatively poorly understood in terms of how that has altered its fire regimes and how that plays into some of the regional fire dynamics. And that's probably one of the most unique, in my mind, attributes of the southeastern US is here we have our most frequent fire region of the whole country, and it's the most poorly studied in terms of history of fire. So here I have a couple different dash lines outlining whatever you might want to call the southeastern US. And regardless of how you cut it, there's very little supporting historical fire data in this region. And these are fire scar records that are from North America. And this is part of the North American Tree Ring Fire Scar Network that is in review by Margolis and others. So there's relatively few supporting records in the southeastern US, despite incredible potential. Here we know that we can develop long records. We know that a robust network across many different sites is possible. There's increasing interest in historical fire regimes, in historical forests and changes in vegetation dynamics, as well as in the past natural and cultural history of the region. So I think going forward, the future is bright in terms of what the potential is for better understanding the historical fire regimes of the Southeast. There's lots of reasons why we would want to expand this information from conservation and prescribed fire of very frequent fire dependent communities to understanding historical people and their roles, as well as disentangling any effects of lightning in this high lightning frequency region. I'm sure we're going to hear lots of information about recent wildfires in the Southern Appalachians. Certainly we could be informing fire risk, fire climate, and fire activity predictions into the future, as well as putting some of this frequent fire regime, maybe frequent fire management into a larger system context in terms of what it means for this part of the continent, land, atmosphere, interactions, as well as any kinds of contributions of this type of activity to the larger global interactions in terms of ozone emissions and those types of issues. But for fire scars in particular and fire history information, I think there's a real need, primarily because of the strong linkages that it has to actual management or application. There's lots of different types of data that we can be using to inform management and ecology. Here they're kind of presented in the top right in terms of different types of records, how they vary at different spatial scales and temporal scales, from studies of microclimate to vegetation plots, maybe forest inventories, all the way up to these long-term and kind of coarse scale records from, say, lake sediments, from pollen analysis. And how tree rings and fire scars fit on this, I think, is very unique in that they provide really a binding proxy across all of these different types of data sources. So they can be compared to plot data, they can be compared to land use history data to really help put all these together into a more cohesive context, which is needed to overcome some of the different shortfalls that these records might have. And then lastly, fire scar data, fire history data like this have tremendous potential for direct application because of their annual resolution. We can be replicating these on small spatial extents, as well as gleaning other types of information about forest change through regeneration and stand dynamics. So what do we generally know? There's a lot of information out here for us to understand fire regimes in the southeastern US. From the charcoal database, here we have the charcoal records from throughout the Southeast. The Southeast has a long record of charcoal in terms of evidence for historical activity spanning through the Holocene. Many of the records show increased fire activity with switches to more agricultural land use about 3,000 years ago, with kind of regular burning activity going forward. Most of the fire scar data is from the 1700s going forward. Some of it actually extends into the 1500s. There's relatively little information from indigenous people. That's certainly a shortfall of some of the fire-related cultural work in the Southeast that could be improved upon. And overall, there's been really little investment, and I mean actual funding or effort to pursue some of the fire scar, fire history determination for the Southeast, especially when you compare it to what's been done in the central US, the Lake States, and especially in the Western US, where most of the fire history data are from. And I think it's so much needed because fire regimes in the Southeast are what I would call a different beast. And here we're talking about the far end of the frequency scale, the most frequent fire regimes, that I believe that there are some very new concepts as well as ideas for fire management and fire ecology that will be gleaned from these frequent or even hyper frequent fire regimes. This is a record at the bottom right of fire events where my pointer is. So all these years along this timeline from 1500 going forward are fire events in this recent study that we completed at the Jones Center at Itchaway. So there's a tremendous amount of fire here from the 1500s up to about 1850 when just after that the forest was cut. But if you look at the left here, we're looking at a mean fire interval for the full period of just over 1 year, and the shortest fire interval being about 3 to 4 months. So this is almost unbelievable in terms of fire frequency. I'm happy to hear that others are seeing this as well in some of their new analyses. But certainly these type of data paint a different picture for fire frequency, I think, for our whole continent. There's certainly potential for frequent fire to exist in the Appalachians as well. There are vast regions, even within the mountain complex itself, that have the potential for very frequent fire. But few studies have really approached some of that variability, especially at the far end of that range, say at the high elevations or very protected areas where we would expect to have less frequent fire. Most of the fire seasonality is in the dormant season. If you're outside of the coastal plain, that dormant season is often split bimodally into peak and fire activity, either in the late winter or early spring. I'm sorry, late winter, early spring, or fall. And then once you get into the coastal play. There seems to be a increasing tendency towards growing season fire. Maybe up to 50% of the historical fires being seen in the growing season. We know very little about historical fire extent in landscape controls. Here in a recent paper that we published in the Cumberland Plateau area, we do see some evidence of fire synchrony in different years. So this is showing in 1829 the different sites that we see with corresponding fire years. We see those fire years also further into the central United States. Here's a more recent data collection we've done just within the Cumberland Plateau. So between these two sites at each end of this arrow, which is about 30 miles apart, 50 kilometers, we saw 11 out of 16 shared fire years between 1834 and the early 1900s. That's a really high percentage of common fire years that we wouldn't otherwise see it at some of our other sites. And then lastly, what we're seeing are some of these maybe ideas that certain landscape features are fire breaks. Those are starting to kind of fall apart in terms of concepts for how fire regimes may be divided. So we see some evidence in the Cumberland Plateau for some of these historical fire events to just move right over some of these 100 to 200 foot shear walls through the historical fire record. Okay, and I should probably end here in that what do we know about historical fire and climate? One thing we see, especially in the Appalachian mountain range, is that elevation is likely positively related to the historical frequency of fire. And we would expect that because as you increase in elevation, you have cooler temperatures overall, which relate to lower productivity and lower opportunity for fire throughout the fire seasons. If you look at the fire history records in the region, there's really little association between fire event years and associated drought. Overall, there's little association, which is kind of surprising. Although some sites do show that, overall, there's very little association. In the region, you know, I guess as kind of the climate condition as a humid continental climate region, there's really little evidence for multi-year droughts or even longer droughts in recent centuries. I think that is a reason why we see a lack of a consistent relationship between fire occurrence and drought. And then in addition to that, we know that there's a historically important role for human fire ignitions in the region. In addition to human fire ignitions and very frequent fire, those types of influences can mask the relationship that fire activity may have with any kinds of climate conditions. Okay, so I do want to save time for questions, so don't look, because I'm going to fast forward through all the other slides I had and just go ahead and thank some of the funders of this work, particularly the U.S. Forest Service Northern Research Station, the Daniel Boone and Chattahoochee National Forests, the Jones Center, especially Seth Bigelow, who worked with me there, the Shortleaf Pine Initiative, the Nature Conservancy, the Tennessee Division of Natural Areas. That's all I got.
Okay, thanks so much, Mike. Really interesting stuff. I've seen your maps come out over the years, and I think they're amazing.
Thank you.
Unless I'm not seeing it correctly, I don't see any questions in the Q&A. But if you guys want any questions for Mike, you can write them into the Q&A in Huba. But I kind of have a philosophical question.
Okay.
You know, there tends to be this disconnect between what like a natural fire regime is and like whether humans are, I guess, considered part of that natural fire regime. And I mean, do you have any thoughts about that?
Well, you know, I think it's just semantics in some ways.
Sure.
Humans have certainly been around long enough to influence the vegetation that we, dominant enough to influence the vegetation that we may consider our earliest known vegetation conditions. And so, so certainly they're important for the ecology of what we have today. And so that's maybe one little cracker to chew on. And then the other would be that going forward, we can't rely on lightning to manage our fire regimes. And so going forward, we are part of the solution to keeping fire regimes. So I think we should maybe chew on that cracker as well.
Yeah, I like it. I like it. Thanks, Mike.
Okay.
Yeah, much appreciated. Yeah, so we're at 1:20 now, so we can move over to Matt Reilly. Matt, you can go ahead and start sharing your screen. Matt Reilly is a research forester with the U.S. Forest Service in PNW. So yeah, Mike, Matt, I'll let you take it away. Thanks.
Okay, great. Can you see my screen? It's still loading here, but.
Yes, I do see it.
Okay, great. I'm just gonna go on faith that my slides are advancing, but if they're not, please do speak up if I get jumbled. Okay, great. Well, thanks, Louise, and thanks everyone for joining this morning. Today, I'm gonna give a quick overview of landscape drivers of burn severity during the 2016 fires in the Southern Appalachian Mountains. And this has been sort of an ongoing side project that was funded by a small ORISE through the Southern Research Station. And I live and work in Oregon these days, but I have a deep love and appreciation for the Southern Appalachians. And I'm just sort of grateful to Steve, Louise, and Joe for sort of keeping me in the loop and keeping me involved. And so we just heard from Mike, obviously fire has a really, really important historic role in the Southern Appalachians. This region is known for its diverse forest composition. I think Robert Whitaker back in the 50s really first sort of pointed this out, that these vegetation and forest types really vary strongly with the complex topography and environmental gradients. And historically and today, fire was another really important driver, sort of driving vegetation with topography driving fire. And there's this really, really unique tight relationship, I think, between the three, where we see that fire was most frequent at lower and middle elevations and really reinforced underlying gradients and strengthened that relationship between environment and vegetation. So a long period of fire exclusion, sort of starting, I guess, in sort of the earlier mid 1900s. Most of the region's been logged, and loss of the American chestnut has really altered species and fuel composition across the region. And the cumulative effects of this have been this compositional shift towards more mesic, less fire tolerant species. There's been relatively little work on patterns of burn severity in contemporary wildfires. There haven't been a whole lot of wildfires to work with. But what we found in some of that work is that we generally see this correlation with topography and vegetation and fire severity. And so, these 2016 fires are really the first widespread fire event the region has seen, and they present a really unique opportunity to take a closer look across multiple fires at patterns and drivers of burn severity. So I have three main objectives today. The first is to provide some context on the 2016 fires in terms of size and area burned compared to recent fires, and also climate during 2016. I'm going to give a quick assessment of the area burned among forest types and how patterns of burn severity vary among forest types. And then finally, we're going to take a look at topographic drivers of burn severity in 5 of the largest fires from 2016. And so wildfire activity has been increasing in the Southern Appalachians. Here's just a figure 1985 to 2016. You can see 2016 there in the red. The fall was really a huge year compared to previous years. There were a couple bigger years, the early 2000s. 2007 was a relatively big year, but certainly nothing compared to what we saw in 2016. And this is the Southern Appalachian region I'm referring to here includes, Eastern Tennessee, Western North Carolina, South Carolina, Georgia, and Alabama. So 2016 really, really sticks out in terms of area burned. We can also take a look at fire size in 2016. And what I have here is just the size class distribution of fires, size class on the x-axis, and then the percent of all fires on the y-axis. And prior to 2016, most of the fires were really relatively small, 500 to 1,000 hectares in size, occasionally reaching greater than 5,000 hectares. But we see in 2016, much, much larger fires. I mean, I think 2 of these fires were greater than 10,000 hectares and a handful were greater than 5,000. So when we think about 2016 in terms of contemporary years, it really sticks out in terms of area burned and the size of the fires. And I think one of the main reasons behind that was this really, really unique acute late fall drought in 2016. I think it stopped raining in September and didn't rain again until winter. And so this really, really hot, dry period. And what I have here to put that 2016 drought in context is the Palmer Drought Severity Index going back to the early or the late 1800s, 1890s. And these are anomalies. And so anything that was wetter than average is in the blue and has a positive value. Anything that was drier than average is brown and has a negative value. And you can see that 2016 was certainly anomalously dry, but it wasn't necessarily the driest or the only dry year that we've seen, either in sort of recent years since the 1980s, or looking further back. And what I have here are fire years, and Steve Norman has been going through the Library of Congress's U.S. newspaper directory, old newspapers and things like that. And we don't have areas for these fires, but what he's done is he's pulled out the years when there were large fires that were noted in those resources. And you can see that there is some sort of association here with these fires and Palmer Drought Severity Index. And 2016, while anomalous, was not necessarily unprecedented in terms of drought when looking at PDSI at least. And so the other thing that happened in 2016, there were hundreds of ignitions across the region in late October and early November. And, most of these were successfully contained, but a handful, generally in more remote or topographically rugged areas, grew to much larger sizes than we've seen in the past, 5 to 10,000 hectares. And what I have here is just a daily progression map of some of the largest fires. A map of sort of where they occurred. And if you look above, what you can see is there's some peaks in terms of when lots of area burned. And so in early November, these fires were burning, and then things really ramped up in the first couple of weeks and slowed down a little bit. Most of those bigger fires sort of attained most of their size during that period. And then in late November, this Chimney Tops 2 fire up in the Great Smoky Mountains was really unique among these events in that it was driven by one of these mountain wave events characterized by really, really high wind speeds that came down from the ridge along the Smokies and really drove, rapid fire progression down into Gatlinburg. And so that fire really, really sticks out in terms of these 2016 fires. Moving along in terms of our objectives, the next thing I'm going to do is take a quick look at area burned and patterns of severity among forest types. And in order to do this, we use the relative change in the normalized burn ratio and some derived thresholds from pre-existing works that I've done in Linville Gorge based on a composite burn index. We use growing season Landsat composites in Google Earth Engine to make the maps. And generally, I just sort of wanted to walk you through some of the different fire effects we see within the ranges of these thresholds. And so, at very, very low and low end, we might see, some litter consumption, some small shrub mortality, but very little tree or overstory mortality. Moving up into the moderate level, you might see more complete shrub top kill, some overstory mortality. And then this high range, where we start seeing, really, really high percentages of canopy trees killed all the way up to, what we would consider a stand replacing disturbance. And so just looking at some of the patterns here of burn severity across four of the largest fires, we have the Rough Ridge and the Rock Mountain. These are the two that were greater than 10,000 acres. You can see that really the vast majority of the area burned was either low, very low, or no change according to the remote sensing. We see some small patches of high severity surrounded by moderate severity, but they're generally very restricted. The smaller Tellico fire, we see sort of similar patterns. Couple high severity patches up on ridges and things like that, but mostly really, really low severity. And then the Chimney Tops fire there, just about 6,000 hectares. So not as big as those other North Georgia fires, but obviously a much greater proportion of high severity fire there on those south-facing aspects where the wind really drove the fire. So a lot of variability in terms of landscape patterns of burn severity among some of these bigger fires. And if we look at cumulative area burned by forest type, what you can see is that these sort of drier, lower elevation, mid-elevation oak forests were sort of the big winner there with, I don't know, 80 or 90% of the area burned. And these come from an older forest type map that I guess I do not have a ton of confidence in. It's from the 1996 Southern Appalachian Band and Biosphere program, so it's potentially a little bit outdated, but it's the best I had, and so I went with it. And so after oak, what you see is much smaller proportions in these moister white pine, hemlock, hardwood forests, mixed pine hardwoods, up there again with that, and then smaller proportions in yellow pine and mixed mesovitic forests, those sort of richer, more diverse cove forests experienced about as much fire as the yellow pine, which is made up of Virginia pine, Table Mountain pine, pitch pine, those sorts of things. And if we take a look at the cumulative patterns of burn severity by forest type, these are across all fires across the Southern Appalachians. We see really the vast majority of the area, 70 to 90% at the regional scale, dominated by this unburned to low class. So really, really low severity fires altogether. We see slightly greater proportions of moderate and high severity fire and some of the other types, particularly the yellow pine type, 6.5% high severity fire. I don't know what my expectations are based on, probably my own biases, but I guess I would have expected much more than 6.5% in those yellow pine stands. Places like mixed mesophytic forests that are generally moister, have more fire sensitive species. These were more similar to yellow pine than the oak at about 6% high severity. So that's a little bit higher than I would have expected. Same with white pine and hemlock hardwood there. And so moving on to the final objective, looking at topographic drivers of burn severity in 5 of the largest fires from 2016. And so what I did was I took the burn severity maps for these 5 fires. It's the Rough Ridge, Rock Mountain, Baudelaire, Chimney Tops, and Tellico fire in Western North Carolina. And I got digital elevation models for all of those and derived different topographic variables, including aspect, slope, and this topographic position index. Essentially, low values there down -20 are generally moister coves, ravines, and things like that. And it ranges up to a high of 20, which would be your upper ridges, drier ridges, and things like that in brown. And so I basically put out 5,000 random points with about a 300-meter buffer between them to avoid spatial autocorrelation, and sampled each of these rasters and then ran them through random forest, which is basically a machine learning algorithm. It's pretty commonly used for these sorts of analysis, and it doesn't necessarily give p-values or equations that we can interpret, but what it does give is it ranks variables in terms of their importance. So in our case, what are the most important variables driving fire severity? And it also provides these partial dependence plots, which allow us to examine the relationship between these different topographic factors and burn severity, basically while holding all the other factors the same. And so a quick look at variable importance. Altogether, the model explained about 40% of the variation. And we see the first thing that pops out is most important is fire. And basically, we see large differences among fires, which is a huge surprise given that chimney tops 2 fire and the wind-driven behavior we saw there. And then what pops out is this topographic position index is really high. And then aspect and elevation following that. And then below that, we see slope and forest type. And so this x-axis here, this increase in mean square error is probably the best measure of variable importance. And it basically shows how much our model accuracy decreases if we leave out that specific variable. Moving along to compare sort of average fire severity among fires, we see the Baudelaire, the Tellico, the Rough Ridge, and the Rock Mountain, all really very low, just above 100 there in terms of RDMBR. So really low fire severity, but this chimney tops 2 is, up there at 300. So probably 3 times is severe on average. If we look at the role of topography, these are each of those individual variables, and these are the partial dependence plots. And you can see that this topographic position index, -20, those are generally our cooler, moister sites, ravines and things like that. We see this really abrupt change as we get to drier ridges with TPI. Aspect, we see a strong signal as well. The sort of southeastern facing slopes really popping out. Elevation is a little bit more confusing, I think. I think what it's pulling out is maybe 2 series of ridges, a lower series and an upper ridge. And then slope, we also see increasing burn severity with slope. And if we just take a couple of those and break them out by fire, it's really interesting. And we see this topographic position index, a very similar relationship between those 4 fires, Rock Mountain, Baudelaire, Tellico, and Rough Ridge. That transition, between about 0 and 20 topographic position index, whereas, the chimney tops fire was just more severe altogether. It has sort of a similar relationship there, but gets up to much higher levels of burn severity, particularly on those upper ridges. And then finally, aspect becomes really important in that chimney tops 2 fire with those winds coming from the south and driving them, not so much in the other fires. So just some brief summary and conclusions. The 2000 fire 16s were certainly unprecedented in the recent record, but not necessarily historically. And what we saw were primarily low and moderate severity fire, even during this extreme drought. With less variability among vegetation types than I would have thought. Very strong bottom-up role of topography, topographic drivers. And, I think my main conclusions are that fires will likely reinforce the underlying gradients that structure vegetation to begin with in this region. And so with that, I can take any questions. I see my talk is still loading.
Thanks, Matt. That was great.
Hopefully you saw my slides.
This is a quiet crowd, can I just tell you? There's a lot of people on here, but no one's asked a question yet. But I think what's really cool, especially about that picture, is like it really shows like how sort of low severity it was, right? Like a lot of those, fires. And by the way, Matt, we're going to go out and sample again next year is the plan. So
Louise, can we ask questions over the mic?
That's fine with me. Yeah.
Sure.
So Matt, I was just going to ask, and looking at the image of severity on the chimney tops fire, and you could see how the direction of wind really drove things. So areas burned at high severity where it was being pushed uphill with a head fire, likely. Did you think about some way to try and incorporate wind direction within the fires?
Yeah, I think, there's RAWS data. I'm not sure what's available, but there are gridded wind data sources from GridMet that are sort of, you can go back in time and get those gridded data to look at. They're also very coarse. I think some of those are, 2.5 to 4 kilometers in scale. But I think, you know, in this situation, we know that there was the wind here and that Chimney Tops 2 fire. And what would be really interesting, I think, would be able to potentially look at variability within that fire and wind. And, you know, I wasn't there, so I didn't experience it, but yeah, that would be great to more directly incorporate that as a driver.
Like a wind speed and direction. Yeah.
Yeah. I don't really know what happened in those other fires. I'm sort of doing this from afar. I noticed a question from Rob Klein. Do you have a sense of how severity level proportions in the lower severity have changed since? Yeah, so we do. I didn't show it here, but we've been working on this delayed mortality method with the RDMBR. And I have another talk later in the week where I'm going to show some of that data. And yeah, that sort of low or unburned, we see large shifts sort of from that into sort of the low. And I think we validated it with some of the field data that Joe and Louise have. And, you know, lots of the oaks sort of blinking out, that they don't have a huge spectral change, but enough that Landsat has captured it. And, you know, I think if you were to look at those maps, the best way to communicate the changes in the patterns is it sort of makes Swiss cheese of those lower unburned patches. But yeah, pretty widespread, not changing the severity of the fire hugely, but really having widespread effects and with important ecological implications.
All right, thanks, Matt. I think we got to move forward to Marcus's presentation. So thank you so much. And Marcus, this is a pre-recorded presentation, but Marcus is on. So if you do have questions, please stay on, or, you know, write them in the Whova, or if you're able to speak here, you can. So Marcus Williams is the meteorologist from the USDA Forest Service here in Athens, Georgia, and he'll be talking today about those wave events. So that was a good segue.
Hi, my name is Marcus Williams. I'm a research meteorologist for the USDA Forest Service Center for Forest Health and Disturbance. Today I'll be discussing high-resolution modeling of mountain wave wind events in the Southern Appalachians. I'd like to acknowledge my co-contributors, Craig Ramsayer and David Hotz, and mention that this research was funded by the UCAR Comet Outreach Program. Mountain waves occur when stable air is forced over a topographic barrier, such as a mountain. The non-convective wind events can lead to large tree falls, power outages, and property damages. These winds are non-convective because they're not generated from thunderstorms. The terrain-induced winds represent 6% of all non-convective wind fatalities in the United States. When strong southeast winds occur, a stable boundary layer, a varying wind profile, which means that the wind turns clockwise with height. When these ingredients are expected over the mountains, it increases the possibility of mountain wave wind. A phenomenon known as adiabatic warming occurs in the central and northern Great Tennessee Valley when these mountain wave events happen. It just means that as the air descends, it warms. Mountain waves can transfer momentum from the upper atmosphere to the surface, resulting in wind gusts in excess of 40 meters per second, or 80 miles per hour or more. When low pressure is present in the Ohio Valley, that generally induces southeast flow in the Southern Appalachians. As you can see here, winds from the southeast interact with some of the higher elevation parts of the Southern Appalachians, and this is something that can create mountain wave wind events in the region. Here's a look at some damage that was believed to be done by a mountain wave wind event. You have the roof torn off the school, and you have several trees down. This occurred in Camp Creek, Tennessee. This is one of the places where the National Weather Service is able to pull observations of these winds from. You had no students were injured during this. You had highway wind event that was believed to be caused by mountain waves, caused some property damage and tree fall. The high winds generated during mountain wave wind events often lead to dangerous traffic conditions and road closures. These images were taken from the Great Smoky Mountain National Park during high winds that were believed to be caused by mountain waves. Mountain waves are frequent through late fall through early spring, so November through March. They peak in December most of the times, and sometimes you have these mountain wave wind events that kind of coincide with the fall wildfire season in the southern Appalachians. You can see on the bottom left, this is a number of ignitions of wildfires, occurrences of wildfires. You see a peak during late fall and wildfires. So sometimes these mountain wave wind events align with the fall wildfire season. One famous case of when you have a mountain wave wind event during wildfire season happened the Chimney Tops 2 fire. This fire started as a small 50-acre fire. An approaching cold front generated mountain waves that interacted with the existing wildfire. The fire was able to grow to 17,000 acres. Unfortunately, there were some fatalities. About $2 million of damages occurred during this event. This research has a couple of main objectives that it's attempting to achieve. One of the main objectives is to identify potential case studies of mountain wave wind events in the southern Appalachians. We're going to base these off of observations, local storm reports, and if a high wind warning or advisory was issued by the National Weather Service. Right now, the NWS has identified 46 potential cases that we're going to be able to simulate and model. So we're going to use machine learning to model and identify the leading nodes of variability associated with mountain wave wind events. So this is basically saying that we want to be able to use a type of machine learning to identify synoptic weather patterns that are often associated with these mountain wave wind events. Also, from the 46 cases that we have established, conduct high-resolution simulations of the case studies using numerical weather predictions. And one of the things that we hope to gain from this study is to kind of improve the forecast and lead time of these mountain wave wind events. As you can see, when these events occur, property damage happens. You have road closures and tree falls in the event that there's an existing wildfire on the ground. So we want to be able to improve the forecasted lead time of these wind events. Also, we want to be able to determine the spatial extent and magnitude of these mountain wave wind events. I'll probably get into this later, but right now, there's only 2 places where observations are available for this. So the National Weather Service really doesn't have a clear idea of the spatial extent of and magnitude of these mountain wave wind events. It's relying on 2 observation stations. One is Camp Creek, where the elementary school is located, and I think we have another observation station in the Great Smoky Mountain National Park. But we need a better idea of how widespread these events are when they occur. Based on observations taken at a meteorological tower in Camp Creek, and also another tower at the Cove Mountain area, the National Weather Service has identified 46 potential mountain wave wind events from 2009 to 2018. These events are stratified into 3 categories: high-end events, moderate events, and low-end events. High-end events are where winds of 90 miles per hour or greater have been observed. Moderate events, which is the bulk of the cases, are winds between 70 and 90 miles per hour. And you have low-end events with winds less than 70 miles per hour. One of the real problems that the NWS has is that, these events are relying on only 2 observations. So, again, they really have no idea of the true magnitude and spatial event of these mountain wave winds. Here's a look at the mean sea level pressure during mountain wave wind. One thing you're gonna notice is that low pressure in all three cases is present in the Ohio Valley area. As you go from low end events to high end events, you have a stronger area of low pressure, which is going to increase the pressure gradient. In all these images, you have southerly flow, but again, normally when you have a stronger low pressure system in the Ohio Valley, you tend to get stronger mountain wave wind. So this is what we think is occurring during this wind event. We're going to use machine learning to get a better idea of what the pressure field actually looks like during this event. That will be done through the use of self-organizing maps. So self-organizing maps, or SOMs, are used to identify and classify nodes or clusters of large-scale atmospheric conditions that lead to the variability observed at a particular point. In this case, we will use surface pressure. So using existing reanalysis data, we're going to use self-organizing maps to find a representative day for each mountain wave wind event classification. So that's your high-end events, your moderate events, and your low-end events. So what does the pressure field look like for each type of event? We're going to use self-organizing maps to kind of representative weather pattern or pressure field for each event. A high-resolution modeling will be done through a process called numerical weather prediction. Basically using mathematical equations to understand how the atmosphere works. Physical processes can be represented through mathematical equations. These equations are solved at designated latitude and longitude grid points that are equally spaced. Now, if you're given information about the initial state of the atmosphere, a future state can be predicted through solving these mathematical equations for it in time. An example of this would be if you put a beach ball in the river, and you know information about how fast the river is flowing, direction of the river, you can predict where the beach ball will be at some future date or time, pretty confident. The NWP model that we'll be using for these high resolution simulations is called the Weather Research and Forecasting Model, or the WRF model. We're going to be using version 4.2.2. This model is fairly used in the meteorology community. We're going to feed it some initial information about the atmosphere or initial and boundary conditions through existing analysis. The horizontal grid point for the one of the first steps we would take to see if the WRF model has the ability to correctly simulate some of the general features of mountain wave wind. We will take a quantitative look at observed pressure versus model pressure. We're doing this because these wind events are largely driven by pressure differences. On your left is the observed pressure, and on your right is the model pressure. Some of the features we're looking at, you can see that off the coast of North Carolina, there's a high pressure. The placement is good as far as the model producing the high pressure system. Also, if you look at the lines of constant pressure called isobars, these are the red lines in the observed map and the blue lines in the model map. They line up pretty well. So we feel confident that the WRF has the ability to simulate some of these general features of these wind events. Again, we're looking at the same time during the Chimney Tops 2 fire, which is around 7 p.m. local time. On your left, you have the 850 millibar pressure level. And as you go from left to right, you go from 850 to 700 to 500 millibars. You can see that you have a varying wind profile What that means is that your winds are turning clockwise with height. The model was able to capture this feature during the chimney top to mountain wave wind event. This slide demonstrates the ability to produce high resolution simulations of these mountain wave wind events. The National Weather Service runs an operational model to help with their forecast. That operational model is run at about 10 kilometers horizontal resolution. If you recall in my previous slide when I mentioned that these numerical weather prediction models have horizontal latitude and longitude grid points. The 10 kilometers is not enough to resolve some of the key features of the mountain wave wind event. These features will help determine the spatial magnitude and extent of these wind events. As you can see on the top, this is a simulation done at 6 kilometers. You can see a broad area of high winds, but you don't get any real details. You don't get any additional information about where the peak winds are, where the greatest magnitude of these wind events happen. To further present the case for the need for high resolution simulations, we're looking at a simulation from the chimney top to fire again. This is around 7 p.m. right before the rapid fire spread happened. You can see in this highlighted yellow box on your left, you have an assortment of wind speeds. The arrow is pointing to where the Camp Creek observation location would be. And this is something that the National Weather Service relies on to get a sense of if a mountain wave wind event is happening. In this particular event, the Camp Creek observation station would have missed on the higher wind speeds to your left. So it might have missed the developing mountain wave wind event. So it is important to kind of have as much detail as possible during these mountain wave wind events. Another feature I want to show you, the shading designates the relative humidity. I mentioned adiabatic heating, and you can see some of that is going on where you're going from very dark green shading on one side of the mountain, and on the other side, the relative humidity is almost at 0. So you have adiabatic heating that's also being picked up during this time. The summary, we briefly illustrated that the destructive chimney tops 2 fire was aided by mountain waves. The model was able to capture some of the features during that event, and higher resolution simulations can help capture some of the local features that might be missed through operational models used by the National Weather Service or models run at a coarser resolution. We identified 46 case studies based on 2 observations. With those case studies, we want to determine what distinguishes one case type from another. So what distinguishes moderate mountain wave wind events from high end. We're going to use the numerical weather prediction of the WRF model to determine the true magnitude and extent of the mountain wave wind event. Thanks for listening. Any comments or questions? I can be reached at the email listed on the slide. Thank you.
All right, thanks, Marcus, if you're on there. We maybe have time for one quick question if somebody has something.
Can you hear me?
I can definitely hear you now. I posted a question in the chat if a lot of people actually knew about mountain wave events. I didn't really know about it until you talked about it until the 2016 wildfires.
Yeah, well, it's something that happens quite frequently. I think they get like 10 to 12 a year. And like I mentioned in my talk, they kind of align with the fall wildfire season. So if you do have a wildfire on the ground, instead of kind of containing it, it might be best to kind of take some more aggressive measures to put it out.
Right, right. All right, anybody else? Marcus has been very quiet. This is a very quiet group.
This is Rob. I've got a question. You talked a little bit about the timing aligning with the fall fire season, and I wonder how, how good of records do we have of the timing, and what can you say about that?
Well,
occur in the winter time.
You said they seem to occur in the wintertime?
Yeah, in East Tennessee, where I'm at.
Well, I think that's one of the reasons we're kind of pursuing this analysis. We just don't have the proper, station data or measurement places to kind of get the true magnitude and extent of when these occur. They're kind of relying on two areas to see. So I think from everything that was communicated to the NWS, yes, they do occur in the wintertime, but I think that they peak in the fall. So maybe like late fall, early winter, like November, December is when you have the peak magnitudes of these events. So they do occur in the winter, but I said late fall, maybe November and December is when you get the most frequency of these events.
Yeah, that's a tough time, especially if our fire seasons are becoming a little bit longer on that fall end. So.
Yeah. I mean, that is quite possible.
All right, thanks so much, Marcus. We got to keep going here to the next person, but thank you for being on.
All right, thank you, no problem.
Yep. All right, Adam Coates is next. Adam, you can go ahead and start screen sharing. So Adam is an assistant professor at Virginia Tech University. He's a fire ecologist, and he's going to be talking a little bit more about on the fuels end of things. All right, go ahead, Adam.
Awesome. Well, can everybody hear me okay?
I can.
All right, good. Well, yeah, thank you very much for letting me be a part of this. It's awesome to be able to be in person at these events, but it's equally awesome to just be in the same Zoom platform with everyone too. So appreciate everybody being a part of this talk. And what we're going to cover is fuels, just simply looking at fuel loadings, so some changing dynamics and managed and unmanaged portions of the Southern Appalachians, and stretching just a little bit into the Central Appalachians as well. So to look at, it's really two projects, and it'll be separated into two research papers that we've been working on, one that's already published and one that's currently in review. We're talking about Great Smoky Mountains National Park in the sense of the portions of the park that we were looking at had recently been unmanaged and, to our knowledge, had not had major impacts from wildfires during a 15 to 16 year period of time. And then we were actually looking at the George Washington Jefferson National Forest, where we're looking at units of and portions of that forest that had been managed in silvicultural management, and then seeing kind of when those systems, when they're still in process, how fuels may have changed as a result of those practices. So why emphasize fuels? From the sake of all of the reasons we could think about this, I think it's to, of course, we're thinking about reducing hazardous wildland fuels. We want to, in some cases, restore vegetative composition. And in some cases, I think I often describe reducing hazardous wildland fuels, but also when we're restoring certain vegetative composition, especially when we're thinking about prescribed fire, we want to ensure that we have the right types of fuels there to promote the type of fire we want to promote if we're using prescribed fire. And so think about the maintaining desired conditions when we're thinking about a maintenance phase and using prescribed fire with that particular fire frequency in mind. To promote specific wildlife habitat, even those that are terrestrial and are actually using coarse woody debris for their habitat and nesting needs. To understand successional and natural disturbance dynamics, and then some recent work that we had done that I'll have references for at the end, and probably won't talk about much in a 15-minute session. It's just some results we saw from the coastal plain with long-term periodic prescribed fire use. We're seeing improvements in water quality, not just from kind of a dissolved organic matter and dissolved organic carbon standpoint, but also when those materials are treated, actually seeing that disinfection byproducts and things that might be housed within the treatment phase of water quality, we're actually seeing reductions in those as well. And so kind of wanting to eventually long-term, you'll see in the end that I'm hoping we build a case for that in the Appalachians as well, where we're using fire in a frequent fashion. Maybe another potential objective, if you can be mean like me, is that we're testing survival of the fittest with some of the research technicians that have done some of this work, crawling under rhododendron and mountain laurel and passing out apparently, because one of my technicians actually sent me this picture a couple summers ago, and I think he just gave up on life after doing lots of Brown's transects. If you've ever done those, you'll understand. So to think about Great Smoky Mountains National Park, again, this paper is currently in review of Forest Ecology and Management. We were looking at locations in kind of the western portion of the park that had not been affected by significant wildfire activity over a 15 to 16 year period of time. And in 2003 to 2004, about 180 locations within the Smokies were included in a 1,000 plot study of the whole Southern Appalachian region, looking at how are fuels distributed across different landscape positions, where they're seeing any trends related to the Southern Appalachians, thinking about overstory basal area, ericaceous shrub cover, and fuel loads and depths. All of those things were related to, I think at that point in time, there was some interest in actually looking at how remote sensing and imaging could be used to determine and make some approximation of fuels, particularly from a management standpoint. And so over a 15 to 16 year period of time, around 2019 was when we took on the opportunity to go back and reevaluate some of the dynamics that were present at these locations in Great Smoky Mountains National Park, really to look at vegetative composition and structure to see how those may have changed over that period of time. Of course, with hemlock woolly adelgid and southern pine beetle having really entered the park in a significant way over the course of this 15 to 16 year period of time, we wanted to see how these dynamics may have changed with basal area and vegetation dynamics, including ericaceous shrubs, and then also the coarse woody debris dynamics. And then there was that additional interest because we did have such a significant wildfire season in 2016, particularly emphasized in this area with the Chimney Tops 2 incident that's already been described. And so in 2019, we had the opportunity to go back to approximately 40 plots. I think the students tried to locate about 50 plots, but we weren't 100% confident that they came back to the exact right locations. And so we felt really confident with the 40 plots we included. To look at basal area with a particular emphasis on hemlock with what was standing and live and then actually was standing and dead. We did tallies of those, thinking about fuel loads and depth with a particular emphasis on coarse woody debris. And then our ericaceous shrub cover we were interested in, primarily mountain laurel, but also rhododendron was noted when it was present as well. We included in there from the Waldrop study that was done with all of the locations in the Appalachians, we wanted to include some determination of both elevation and moisture regime or a site condition, including xeric, intermediate, and mesic plots, to see if that actually had any influential determination on any of these variables we were measuring, and to just see how these things had changed over time. And of course, we thought in a large sense that there would probably be increases in particularly standing and dead eastern hemlock. You'd see increases in some of the fuel loading and actually probably some increases in woody fuel depth over time, with also an expansion of ericaceous shrub cover over this period of time. And so the locations we were particularly in to emphasize this is they were the western portion of the park where ultisols and insectisols are particularly noted in that area. And I bring that up because of some of the vegetative dynamics that are present there that I think we're also noting in other studies as well. So for the plots that we used, if you've actually looked at, we did a Southern Appalachian photo guide for fuels, where we used basically the same methods in that. And so as a reference, there's a bunch of the equations that are used for coarse woody debris dynamics when you're tallying fuels with Brown's transects to then get at woody fuel loading. That's the typical method we use. I'm not going to belabor you with all those things and the equations that are used, but there's definitely a reference for that. Within the plots where we actually laid out those transects, we were looking at the overstory trees in a 0.02 hectare plot, and then half of that was used for ericaceous shrub sampling. In 2004, we actually measured the tree crowns to do those estimates. In 2019, we actually just did an approximation of the percent cover of those plots based on just the time and the availability we had to be out there to conduct the work. So some very global changes that we saw to think about kind of systematically here with vegetation fuels and then our shrub cover is that we saw that there were no real changes in total or live eastern hemlock basal area or ericaceous shrub cover. But snag eastern hemlock did increase, with the most significant increases on xeric and intermediate sites as elevation also increased. And that range for elevation was about 278 meters to 765 meters. With fuels, there was really no increase or decrease in O-horizon thickness over time, but we did see that overall in both years that the depth increased as elevation increased and xeric depths were greater than mesic depths. Woody fuel depth decreased over time, and we believe that that was most, and I'll kind of point to this in the discussion, but we believe that's probably most related to the initial impacts of some of the disturbances from both southern pine beetle and hemlock woolly adelgid, that those probably had over time, those had actually changed and decreased from that initial pulse of additions due to those insects. The sum of the 110 and the 100-hour fuels actually increased over time, but we didn't see any significant changes in total woody fuel loads, and the 1,000-hour fuel loads didn't actually increase either. So overall, as you can tell, I've kind of thinking about those initial predictions, we thought that some of the fuel loading would have actually increased, and we didn't see that as a dramatic change or dramatic shift over time. Similar results were actually noted based on moisture regime and O-horizon thickness from a study that was done in the northwestern part of South Carolina, so just breaking into the Appalachians on the Chaga ridges. And actually elevation and O-horizon thickness was actually, that trend of seeing increasing elevation and increasing O-horizon thickness was actually noted throughout the Southern Appalachians in the study in 2007, where more locations than just Great Smoky Mountains National Park were included. So the thing I think that is pretty interesting here, and actually Rob Klein contributed so much to this project, from allowing the students to actually be on site and getting them acclimated to the site and working through a lot of the logistics and the thoughts that are going behind this. So I appreciate that he's a part of the talk and will be speaking after me. But I think he would even speak to that even some of these slight changes would be things that would be considered for managers within the park to think about the ecology and the unique dynamics that are a part of Great Smoky Mountains National Park. Particularly, we've been thinking more and more about wildlife that might be reliant on loads and structure of forest floor and coarse woody debris, whether that's in the sense here where we're looking at largely unmanaged landscapes where we haven't had a lot of active prescribed fire in these particular plots, thinking of what might actually be changing just as nature is taking its course over time. And then also the future coarse woody debris dynamics, not only the loads, but then actually the structure of fuels in there that could be occurring as you have the standing and dead eastern hemlock that's falling over time to the ground. So to think about some of the managed landscapes, this is actually a paper that we actually had published in Forest Ecology and Management earlier this year. The location is the George Washington Jefferson National Forest, so actually coming a little bit into the central Appalachians. Location pretty close to Blacksburg, Virginia, where Virginia Tech is located. Again, we're thinking about ultisols here, so kind of that heavy clay composition for soils. This is a long-term silvicultural study that was initially installed in 1995 and 1996, where there were multiple replications included of unmanaged controls, a high retention shelter wood, which was established again in 1995 and 1996. The initial cuts were made, and then the actual shelter wood removals occurred in 2007 and 2008. But the high retention cut and then a low retention cut, and then actually clear cutting where all of the standing vegetation was removed. For this, we actually did a slight modification of how the Browns transects are located, just because coinciding with this, we actually did some other looks at soils, looking at nutrient content, and then actually thinking about overstory composition. For this particular paper, we did exactly the same measurements along the transects, just initially in a different layout for the Browns transects. But again, 50 feet long or 15.2 meters, and then the measurements for our time lag fuel classes along those transects. Very big generalizations here with a lot of numbers with this table, and I hope the numbers are not so small that you can't see. But just to kind of point out some things that we saw is that we actually here did destructive sampling for both litter and duff, and then actually we did a kind of a merger of those to come up with the total O-horizon loading that we would see there. And of course, the control, as we expected, we actually had higher loading of both the litter and duff combined when we were looking at the control plots. We did see that there was not a significant difference, but it was marginally different between the retention systems. That is actually higher with our low retention shelter wood as opposed to the high retention shelter wood. For total woody fuel loads, again, that was kind of this unique dynamics that we were seeing when you actually broke down some of the fuel size classes and looked at the differences between the retention systems for the shelter wood. In some cases, we would note that there were significant differences, but then others where it would just be marginally where one would be different from another, that you weren't kind of getting these exact numbers across the stream. but seeing here that basically the control for the total down and dead woody fuel load was actually higher than all of the treated units. But the second highest one was the low retention shelter wood. For total fuel load, the control was actually greater than all of the treated units. But again, kind of this lingering, there are not all equal across the board, with kind of the high retention shelter wood coming in with the lowest value there, which I found to be kind of interesting just from the sake of the material being removed. And when you think of the dynamics that might be present in harvesting and how, some of the overstory dynamics could be shifted when you actually leave some of the shelter in place and then actually choose to remove that long term. Are we seeing longer lasting effects from choosing to do different systems of retention? For the total fuel load altogether, I think one of the questions that we had going into it was, would the clear cut actually show the lowest values across the board? And we actually didn't see that, with actually higher 1 hour fuels and 10 hour fuels being present at those for the clear cutting itself. For fuel depths, we saw that O-horizon thickness was greatest on the control, and that woody fuel depth was highest on the control and actually lowest on the clear cutting, with again some of these kind of marginal differences being present for the shelter wood systems that we had. Different metrics for retention was a part of those. So for that particular study, the control loads and depths, I think, was something that stood out to us. Of course, that was something that we kind of went into predicting, that a lot of those loads and depths would probably be highest for the control. I think those differences between the shelter wood, actually seeing that there could be longer lasting, even if they weren't necessarily specifically, statistically significant, when you have, some of these differing depths of litter and duff, and actually reaccumulation of those in a seasonal nature. Kind of what would that look like if you actually chose to do some type of burning in those treatments long term, if there was kind of this thought that prescribed fire would become a part of those systems after you had done some of the shelter wood harvests originally. For clear cutting impacts on fuel depth, this was sustained, since 1995 and 1996. And actually seeing when those removals were done, that 1 and 10 hour fuels, you were seeing some sustained differences in those. And I think one of the questions that was one of the graduate students that was the first author on this paper, just thinking of the follow through with, in any case where some of these systems were actually enacted and then there was kind of a delay in actually following through with those treatments, which often happens due to markets or anything else that might be related to making those decisions to delay a final harvest. What actually happens if you decide in that period of time to do any type of prescribed fire, or you're thinking about prescribed fire long term, kind of at a stand initiation phase. So of course, with both of these studies, we're looking at the dynamics of natural disturbances when we're kind of thinking about the Great Smoky Mountains National Park study, and then also the control units with our study here closer to campus in Virginia. I think it's a complex response that you get when you think about the time lag science classes, where you may not see these differences in total fuel load, but when you do break it down and actually think about the different size classes that might be related to wildlife habitat or might be considered for some of our prescribed fire operations, some of this idea of flammability, and I kind of relate that here with the forest floor complexity. We weren't necessarily identifying differences in species or thinking about flammability as might be discussed with some other talks during the conference as a whole. We weren't really digging into that, but I think that's a place that we could go next, and thinking about some of the complexities that would be there that might assist managers as they think about burning in some of these locations. The dynamics with retention, I think, was really interesting and something I would like to think about even more as we go forward with research in this region. Again, seeing these differences in moisture regime and elevation that could be related to both wildfire activity and prescribed fire activity, as was noted earlier in Matthew's talk. And so with these management goals, I think that was one question that I had is, to some extent, if you're actually changing some of these dynamics and you're not necessarily seeing that total woody fuel loading is decreasing, but you are having impacts on these other size classes, does that make a difference for your long-term objectives, thinking about prescribed burning or thinking about managing for specific wildlife habitat? What are you actually accomplishing by just kind of looking at total fuel loading? Maybe you're going to miss some of the details that may initially be important for your overall management goals. So as always, my students always complain that I talk too long, so I won't leave as much time for questions as I had hoped. But since this is being recorded, the 2 papers that are referenced here, I highlighted in red. The other citations are here too. And then we've done lots of other work on the Appalachians that I thought would be helpful to leave references for. If anyone is interested, you're more than welcome to get in touch with me to know more of that too. Of course, we had lots of collaborators on this, as I mentioned Rob earlier. Helen Moore with the consortium of Appalachian fire managers and scientists contributed a lot to being able to go back to the Smokies and locate locations from 15 to 16 years ago. And then we surprisingly didn't crush the souls of all of the research technicians that were involved in the work. So to give them a big shout out because they were a big part of both studies. So with that, thank you again for the opportunity, and I'm sorry that I talked too long, but.
That's all right, Adam, thank you so much. Yeah, unfortunately, we do not have time for questions. Perfect timing, Adam.
Okay.
But I'm sure he'd be happy with an email or like a chat through Huba or whatever.
Absolutely.
So, all right, thanks so much, Adam. We're going to change it now to our last speaker on the first part of our session, right? So we have another session after the break. Just continues with this. So our next speaker is Rob Klein. Rob, you can go ahead and start sharing your screen. And he is a fire ecologist with the National Park Service at Great Smoky Mountain National Park. And Rob, I'll let you take it from here.
All right, great. Greetings from East Tennessee, everybody. I'm excited to be a part of this special session. It's great to have so many people focused on Southern Appalachian fire ecology and interested in doing research. That's great. And I really appreciate Louise putting this together. So for starters, I want to start by acknowledging the contributions of my coworkers, Matt Wood, Wiley Paxton, and Allison Arula-Nantham. Without these guys and their passion and hard work, we would know a lot less about the fire effects in our national parks. So I definitely want to acknowledge all their hard work. As another quick note, I realized that I may have overpromised when I submitted my title back in June. So there are probably about 3 or 4 different talks that could actually come out of the title that I have here today. But what I want to emphasize is that the focus of my talk today is to simply describe how we use science to help inform the management response to wildfires in Great Smoky Mountains National Park. And so that's kind of the direction I'm going to focus on with that. And how do I advance the slide? That's not working.
Rob, do you have it on the second screen?
Yeah.
You might need to put your mouse over on that screen and click, or click on your slide one more time and then hit forward on your keyboard.
Okay, I got something worked out here. Sorry about that. Technical difficulties with a virtual conference, imagine that. For those of you who don't know, Great Smoky Mountains National Park is about a 210,000 hectare preserve that straddles the border of the states of Tennessee and North Carolina in the southeastern United States. My overall focus is going to be on the management response to the 2016 wildfire event, the November 2016 wildfire event in Sevier County, Tennessee. But I want to set the stage by providing this overview of the incredibly busy fire season that we had in 2016. I've been associated with fire management in the Smokies since about the late 1990s, and the 2016 fire season was by far the busiest, and we've had some busy ones. 2007 was a busy year too, with that drought we had then. But in 2016, from March to November, we had 20 fires in the park alone. That may not sound like a lot, but the average annually is about 6, and typically a lot of those are pretty small. So a lot more of these were quite a bit more significant and required quite a bit more effort to deal with. And that doesn't account for fires that we responded to just outside the park or in neighboring national parks that are nearby. And I definitely want to emphasize that the fire occurrence in 2016 was driven by near record high temperatures and an extreme drought. The drought, the record temperatures, and the annual leaf fall of the deciduous forest all converged in the month of November in the Southern Appalachians. And the region experienced one of the most active fall fire seasons in recent memory, and maybe in a long recorded memory. The Chimney Tops 2 wildfire was discovered in Great Smoky Mountains National Park on November 23rd, 2016. 4 days later, the fire had grown to a size of about 16 hectares, so still pretty small. It was just kind of creeping around. But on November 28th, multiple fires, including the Chimney Tops 2 wildfire, burned over close to 7,000 hectares in just a single day in Sevier County, Tennessee. About 4,400 hectares burned inside the national park. As many of you know, this was an incredibly destructive and tragic event, and where 14 people lost their lives and over 2,000 structures were destroyed. So an incredibly significant event for us. The wildfires in Sevier County on November 28th were driven, as we've already heard from several speakers, by exceptionally high winds, mountain wave wind event that occur not every year, but almost every year. These winds were measured up to 87 miles per hour, but later estimates by the National Weather Service took that up to, they estimated that the winds were greater than 100 miles per hour in certain locations. This wildfire event is by far the largest in the history of Great Smoky Mountains National Park, more than doubling the size of the previous largest. And perhaps even more notably, more than 99% of the area burned in about a 24-hour period. So this was an incredibly fast-moving and unprecedented event. So the largest wildfire, in comparison to that previous largest wildfire in park history, which occurred in about 2001, burned about 7,500 acres over about 2.5 weeks. So a very different order of magnitude different in terms of the rapidity of this burn. So with the rest of my time, I'm going to shift and talk about some of the resource management responses that followed. And I'm going to separate these into the immediate response and a set of longer term activities. I can advance my slide. Aside from the management of the fire itself in the days after November 28th, an immediate focus of park management was to assess hazards related to watershed response. And this is not something that many of you may think of, but when we have an extreme fire, there can be substantial impacts to overland flow that can cause flooding, and this can cause even more damage to surrounding communities. So it becomes a really critical activity to try to assess the risk of that and to try to mitigate that and take action. So the National BEAR team, and BEAR stands for Burned Area Emergency Response team, was assembled in the park within about a week of the blow up on November 28th. And to identify the flooding hazards, the BEAR team first had to create a soil burn severity map. This is pretty standard with the way the BEAR teams operate when they go to these large fires. And you can see that burn severity map, the soil burn severity map that we created here. This was created using leaf-off satellite imagery taken within about 2 weeks of the burn event. And it was calibrated with observations from over 120 field testing sites by hydrologists, soil scientists, and ecologists. You can see that the majority of the site, and it's about 80%, I think, total, and you see this in aqua blue, was deemed to be low burn severity, while moderate burn severity in yellow accounted for about 16% of the fire area. And this is what moderate soil severity looked like after that burn, which was, I don't think we knew what to expect, but in this case, the O horizon was almost completely consumed, but it left there was a thin layer of mostly charred organic material left on the surface, and the roots were largely intact below the surface, which turned out to be pretty important in terms of soil stabilization as time went on. Soil color and structure were largely unchanged. And so once the BEAR team had the soil burn severity inputs, and they were able to run a series of spatially explicit hydrological models. And you can see some of one of the modeling results here. The team modeled 3 watersheds within the burn perimeter. And the results you see here from the largest of those watersheds, which is the west prong of the Little Pigeon River. In general, the watershed response varied by stream segment, which is, you might expect because different areas experience different levels of severity and also different types of topography. And you can see how those segments differed by the different colors of the stream segments depicted on that map. Most importantly, the watershed response was deemed to be low risk overall, and it was predicted to have little risk to the surrounding communities, which was good. And that moderately enhanced watershed response was predicted to last about a year by the hydrologists that were working on this project, and until the vegetation could recover. One of the additional points I want to make here is how little anyone knew. We had soil scientists, we had hydrologists, ecologists assembled, some really experienced and smart folks to kind of look at this problem after this occurred, and it was amazing how little was known about what watershed response we could expect, or even the soil burn severity that we could expect. And I think that this points to a real need for additional research and publication of regional results regarding these critically important system responses. There's a lot of work that's been done out west, but not really in the Southern Appalachians. So this is just a walkthrough of some of the typical sort of sedimentation that we saw, on the main park road, Highway 441. Pretty minor stuff. Just some sedimentation in ditches and culvert heads. But the question remains is, can we count on similar results in the future? And we don't really know the answer to that. Okay, I'm going to shift gears now and start to talk about some of the longer term management responses, resource issues that we've been dealing with since 2016. Talk briefly about how burn severity mapping has been used to help address those issues. Most of these issues were identified during the BEAR process. And here you can see a list, this is not an exhaustive list of the issues by any stretch, but for the remainder of the talk, I want to focus on 3 of these to just illustrate how the park has been dealing with some of the resource management issues following this event. Those are going to be invasive plants, hazard fuel reduction, and research, actually. I'm going to start by briefly describing our burn severity mapping process, and this is going to be a repeat of a lot of what Matt Reilly talked about. So I'll kind of go through it pretty quickly. For this work, we used differenced normalized burn ratio, or DNBR, following Key and Benson, and that citation is provided on the slide. Just as a quick review, we use pre-burn Landsat 8 imagery from the summer of 2016, and the fire perimeter is outlined in orange. This is the pre-burn image. This is the post-burn satellite image, and you can see now a great deal of contrast between the high and low severity parts of this burn. And this is the unclassified DNBR image, which shows the areas of greatest change. And you can, those high severity sites really stand out on there. And of course, this is the classified burn severity map right here. And this shows how severity varied across the landscape. And I'm not going to spend too much time here, but I will just say that green is unburned to very low. Aqua is low severity. Yellow is moderate severity, and the red is high severity. And a part of identifying the severity class thresholds is to accomplish that, we sampled 52 composite burn index plots, also known as CBI, from 2017 to 2018. And in addition to that, I want to mention here that we 39 of these plots were made into permanent long-term monitoring plots. So we have that, and we also collected some vegetation and fuels data from those plots. So we have a baseline for doing some future work out there as well. Back to the CBI data collection, that data collection followed Key and Benson, again, standard methods. The CBI scores were plotted against the DMVR values to help inform the establishment of those thresholds. And I've provided those in the chart over here to show where those breaks are. And this is the final extended burn severity map. And I'm in the interest of time, I'm just gonna go through, skip over this one here. To bring that map back to the real world, though, I just want to show what some of that areas on the ground actually look like. So this is the very low severity. You can see just pretty minimal effects in the understory. This is low severity. You can start to see a little bit more of an effect in the canopy with a little bit of canopy loss. Moderate severity, we start to see a substantial amount of canopy loss and pretty profound impacts to the stand. And high severity, as we saw earlier, is very similar to stand replacement in most cases. So how do we use these maps? The dealing with invasive plants after an extreme wildfire is a huge problem, and it's one of the biggest management challenges that we have. And it's also one of the most important uses for the severity map, because it can be used as a tool to predict where the worst invasions can occur. Since 2017, nearly 300,000 stems, non-native stems, have been removed or treated. And those most notable invasions are in the high severity sites. Parks vegetation management crews use the severity map extensively. And not just on this fire, but for numerous other fires in the past. We've been making these maps for a long time. They use to plan and prioritize survey sites and also for field navigation. And another critical management response for the park is to learn about the factors that contributed to the unprecedented severity of the 2016 event. And we know obviously wind was a key factor there, but and we want to learn as much as we can about other factors as well and apply that knowledge to the future management of hazardous fuels. So this is another instance where the extended burn severity map can yield important insights that we can learn from. In this slide, what we've done is we've isolated all the high severity polygons within the fire perimeter. And then when we overlay the areas that were mapped is also having the evergreen shrub Calmia latifolia in the understory, we can see a pretty undeniable pattern. In fact, 72% of the high severity patches contained Calmia in the understory prior to this wildfire event. This teaches us a great deal, not only about the nature of Southern Appalachian fuels and their potential, but also about how to prioritize hazard fuel treatments and develop long-term management objectives. And so armed with that knowledge, we can better prioritize how to direct fuel reduction activities along the park boundary and around park structures. Finally, the park has made serious efforts to attract and facilitate scientific research so that we can learn as much as possible about the park's natural systems and the role of fire. Since 2016, there's a wide range of really interesting research that's been done that's either been completed and published or it's underway, looking at things as diverse as mycorrhizal fungi, salamander habitat, wildland fuel recovery. And most of these projects have actually used the burn severity map that we created to help inform their sampling design. So again, another really critical use for that product. And I think the research, we don't maybe typically think of that as a management response, but I want to make the case here that it is. I think it represents a really important management response, and it's essential for educating park managers and the public and just contributing to the advance of science as well. So to close, there are a number of resource management considerations following extreme wildfires, and they can be complex and long lasting. I hope I've made the case for the importance of burn severity maps in kind of helping to deal with some of these resource issues. both in the immediate response and in the longer term response. And finally, I believe there are some really good opportunities for researchers to help improve some of the tools that managers in the Southern Appalachians have. And I think I am pretty close to the end of my time. So that's all I've got.
All right, thanks, Rob. I think that is perfectly on time. So
Wish we had time for questions.
No, I know, but no time for questions. I'm sorry. But yeah, thank you. Wrap up to the session here. Everyone, we will start again after the break at 3 o'clock, and like 3 o'clock Eastern at least. I don't know if Sam, you wanted to say something, Sama?
Yeah, absolutely. Just to close us out, Louise, we're going to be switching the Zooms, so you can meet me in the next Zoom, and we're excited to have all of you who want to continue the conversation as well. Thank you to all of our speakers for sharing their expertise with us today. The session will be available in Whova, our conference app, within 2 weeks after the Congress ends. We're going to take a short 20-minute break before beginning our next set of breakout sessions at 3 p.m. Eastern. There are 6 special sessions, each featuring a great lineup of multiple speakers and topics, as well as our first of 2 virtual field trips. To choose the one you'd like to join, use the agenda tab on the left side of your screen and click sessions. You can also click subsessions for more details about what to expect. To join the session offering Spanish and Portuguese interpretation, please be sure to select the session titled Wildfire Simulation under Future Climate Change Methods and Applications. Thanks again to our speakers, and enjoy the rest of your day. Take care, everybody.